So I want to convince you today that we can describe proof nets in the multiplicative fragment simply by permutations. Some of the ideas in this paper that I'm following, which is just titled Multiplicatives, commonly referred to as Geometry of Interaction 0, are the foundation for the further Geometry of Interaction papers. When I spoke to Thomas Sealer about this, he said, very insistently that this is the paper to start off with. So this is going to be giving us some of the ideas for Geometry of Interaction later on. Okay, so I want to be able to talk about normal forms because what I'm going to say at the end of this talk is if you have a proof net possibly containing cuts and you extract from it a particular permutation, then that permutation is going to correspond to another permutation that you get corresponding to the cut-eliminated version of that proof net, right? So you heard me, I just said the cut-eliminated version of that proof net, so we need normal forms. And we actually get cut elimination pretty easily inside the multiplicative fragment. So let's start there. Okay, so there's only two types of redexes inside the multiplicative fragment. There's axiom redexes and then there's tensor par redexes. Okay, and this is the single step cut reduction step associated to the axiom redex. So this part here is the axiom redex, and this is the reduction step. This is the main computational component of the multiplicative fragment. There's deletion of data, and there's the propagation of the information through the tensor par elimination step is essentially bookkeeping. This is really where the computation lives. I'll explain what I mean by that in more detail a bit later.
Just a question on that.
Yeah, go for it.
Do the original links that AI are a premise of, does AK become the premise of those? So like, yeah, I'm just asking about the rest of the structure, how that links up to the AK.
So if there's something down here and there's something up here, they're going to get conjoined.
Yeah.
Does that make sense? Cool.
So does that mean that there's rewriting of indices within the rest of the proof net as well? That these indices I appear in, or they're only in the links?
Yeah. You don't need to. You're only eliminating the I and the J. There's not rewriting of indices later on because those indices don't depend on the previous indices.
Well, it depends what you'd find a proof structure to be. We're back to this thing in the earlier lecture.
Well,
right? I mean, if it's a set of links, then those links contain these indices in them.
Yeah.
Right?
Yeah.
If it's just a graph, then that's implicit. But if it's a set of links, then you need to rewrite I to K and all those things.
Yeah. Agreed. Okay, cool. The tensor par redex is the following. Oh, does that make sense? With everything above the tree left as it was, this doesn't disconnect the proof net. Just make that observation in your head. I thought maybe it would, but there's necessarily, this is connected to that, and that's connected to that by assumption of the prior being a proof net. So the precise statement is, if this is a proof net, this is still a proof net. So this can't introduce short trips. So
can I just pause to worry about something? So
yeah, go for it.
I mean, the order of the premises here is very important, right? I mean, if A equals B equals, I mean, so yeah, if A equals B, it could connect up the other way, right? But wasn't there two ways of forming the link from AI and BJ?
Yeah, there are. So I wanted to actually eliminate that. So that was something that I wanted to, maybe I should have started this talk with that. I think that that second way of forming the tensor link was actually redundant. Billy and I ended up having a conversation about it, and I believe it's not needed. And I'm now not considering it. The reason why it was redundant was because the order is implicit inside the sequence, right? So the way that I was defining the links was that they were tuples, right? And so you've got the order implicit inside it. So you don't need to further specify that by having two versions of it, right? Mm-hmm. So if you get rid of the second version of it, you can set up the theory exactly the same way that I did, and you lose absolutely nothing. In fact, you gain not having to think about that second case all of the time, right? Does that help? If we want to keep it there, then I think you need another rule here, and that's like really cumbersome, right?
Okay, yeah, I'm happy with the former. Mm-hmm.
Okay, sweet.
Also, this redex looks kind of like you could have cut these together, but for some reason, like they were. Oh, sorry, they are cut. I thought they were tensored in the notes. Maybe I'm misremembering.
No, I think I've got cuts here. I mean, that's kind of, there's many ways in which this is almost the redundant one, right? So an object that I'm actually going to be talking about, which is important, is if you take a proof net with cuts in it, and then you eliminate all of the tensor par redexes, so that you only have these axiom redexes left, right? That proof net is an important thing. From that, you can prove the statement of geometry of interaction really easily. And I just don't see it as a significant step. I see it as like, it's a compression of the information of the atoms that you cut in against each other, right? Mm-hmm. Yeah, because if these top things were atoms, and then obviously the tensor and the par aren't, then cutting that tensor and the par is just a compressed way of cutting the two atoms. It's got the exact same information inside it, right?
Yep.
Yeah. So you just propagate it up towards the atoms, and then you do all the like atom elimination, and then that's where the real computation comes from. Okay. I don't know how to write on these boards. Maybe I'll pull this down and this one up. Okay, and now I can barely reach that board. Okay, we'll see how this goes. Okay, so I want to establish the Church-Rossa property, or in other words, confluence, right? Which is just actually, I guess that holds true for proof structures more generally. So there always exists a pi 4 that you can normalize to. Okay, this is simple.
Well, what the hell are you doing? Can you move that front board up and right on the back board?
Then I need to squat.
Just do it. Just do it. Just move it all the way up. Yeah, I don't need to see it.
Oh, you don't need to see it anymore. Well,
No,
that's
no,
what
no.
I was trying to do. Okay.
Yeah, it's okay. That's not stuck, is it?
All right, I can fix it. Whoa, this board sucks. It's like falling off.
Yeah. Okay.
Not built vertically.
Not optimal, but that'll do.
Okay. Okay, I don't want to say much about this because I want to get through it, but it's really obvious, right? So any elimination step doesn't eliminate any other redx. So there's no redxes that eliminate any others. So if you take a pair of redxes and then you eliminate one of them, then that other one is still sitting there. So now just eliminate that other one, right? And that's literally the observation. So where this gets hard is if you have like a weakening rule, for instance, right? Or if you have contraction or something like that, then one redex, one cut step might introduce redexes or might eliminate other ones, but the system is so simple here that that doesn't happen. So just take your pair of redexes that you did and do one and the other, or do the other and then the one, and then you're done. Okay, so that's it. So now we can get on to defining the different permutations that are related to the graphs. I've been very unoptimal with the way that I've used these boards. Let me move this up, grab the other one, and I'll do it more sensibly from here. Oh, I just got this one. Okay, so what I'm going to say is I'm going to say if you give me a proof net, then we've got a whole bunch of different axiom links, which are labeled by integers, right? So if there's n axiom links, assume that those integers are labeled 1 through to n, and then those axiom links are defining for you a permutation, which is just given by a set of transpositions. Easy. Cool. So that's the axiom link permutation. So the way you can think about that is if you have a proof net, that's kind of like everything that lies above the axioms, right? It's just capturing the data of those axiom links. We could also think about going into the proof, right? So I could say set up a switch in S and then give that to your proof net. And then what we can do is we can say start at the ith atom and then go down into the tree. And then the first time that you come back up to an atom, that's going to be bj for some j. And then we're just going to define that to be the permutation. I gets back to j. And then we just do that for all of them. If we assume that we have a proof net, then that's going to be a well-defined, it's going to be a well-defined permutation whether we have a proof structure or not, but then it's going to be cyclic if it's a proof net. And that's going to end up being our interpretation of the sequentialization theorem. Okay. I can't remember the notation I used. I did it that way. Sweet. Yeah, sweet. Does that make sense? Do we want to have a look at some examples? So this is the set of proof nets that I wrote out for you to show, Dan. If you can share your screen, please.
Yep.
Sweet. So I didn't do any examples of the axiom ones. I think that they're simple enough, but just to make sure that we understand the data one, just go down to...
sorry, I shared the wrong thing. These ones? Yeah,
exactly. So if you just, maybe the bottom right one is going to be the easiest to read because I've set them all to right links. Yeah, so I've just got a simple proof here. And then in blue, I've written RRR. So I've just associated to every single link here, the right switch in. And then we can see that this gives you the permutation 1 through 5, 7. So that's beta, right? So if you look at A
well, can you say what 1, 3? What are the numbers? They start over here. 1, 2, 3, 4, 5, 6, 7, 8. So start at 1 and go down into the body of the proof and then look at where you come up. And that's axiom 3, right? So 1 gets mapped to 3 and then go down at 3 again and go into the body of the proof and you come up at 5. Does that make sense? Yep.
Cool. And so now you can see the sequentialization theorem, right? Like that's going to be cyclic if and only if you have a proof net, because a proof net means that you've got this long trip condition. So we're going around to everything, right? The only way that you couldn't go around to everything is if you had some smaller loop inside your proof, which means that you've got a short trip. Do you want me to do better than that? Or does that make sense?
Well, what's happening with 8 here?
Pardon?
Because there's 8 axiom links.
Yeah, so this permutation that I've drawn here is 1 goes to 3, goes to 5, goes to 7, goes to 1, and then 2 goes to 2, 4 goes to 4, 6 goes to 6, and 8 goes to 8. And it's the same process. If I look at 8, and if I go down into the body of the tree, then I come back up to 8, right? So that just acts identically on the even axiom links.
So wait, what is the thing that's cyclic?
Sorry. What's cyclic is when you compose this with the axiom link permutation, right? So I can write the formula.
Right. Okay.
Yeah.
Because like the whole permutation is definitely not cyclic.
Yeah, sorry, I said the wrong thing. Beta is not cyclic, but the condition is. So also the sequentialization theorem required it to be for all switch-ins, right? So the point is, if you give me a formula that's provable, then I can just look at its type in tree, and that's uniquely determined by the formula. And then what's left is the decision of how I connect the axiom links, right? And those different decisions that I can make are defining for you different proof structures, right?
Sorry, could you say what the type is?
I just mean the formula, right? So take a formula that's provable, A, for example, right? And then if I were to what I want to talk about is kind of like the substructure of the proof structure that corresponds to the proof of that formula, but I'm ignoring the axiom links. So I can do an example.
I think I should stop screen sharing, right?
Yeah. Let me think of a simple example. I can think of a complex example. Oh, this is better. Yeah, I've got one in my notes. Okay, cool. Okay, so let's take a provable formula, and I'm going to tell you that the following is provable. Right? Okay, and then what I want to say is take a proof of this formula, right? And there's going to be many different proofs of this formula, but they're all going to have something in common. But unfortunately, that thing that they have in common isn't quite a proof structure. So I can't say that there's an underlying proof structure that's unique. So I was just trying to kind of hand-wavily explain what that thing that is unique about it. And it's the substructure of the proof structure, which is essentially just the typing tree of this, right? So you can see that the most parent connective here is the par link. So I'm forced to write this. And then I just do the same thing for these two things. The most parent link here is a tensor. And the most parent link here is a par. Yeah, cool. And so this object here is invariant across all of the different proofs of this formula, right? What isn't invariant is the way that I join the axiom links. You can see that I've got two choices here. So one yeah, so zigzags is one of them, and then dashed is another one of them. Does that make sense? Okay, and then the point is, if I have a proof structure that doesn't have only a single conclusion, like you can see here that I have a single conclusion, right? That might not be the case, but that's fine because I can just take the par of all of the conclusions, and then I'll always end up with something that does only have one conclusion, right? And what's interesting is that the if I took the proof net pi that had multiple conclusions and I looked at beta of pi for all the various different switch-ins, I actually get the exact same set as if I were to have taken all of the par links together of all of the conclusions and then looked at all of the betas. The reason why is because the par links don't change beta. So this is an observation worth making.
So just before you get to that, are you saying, so the substructure that you obtain here, are you saying if you take any provable formula and erase all the axiom links, you'll get the same structure?
As long as it's got one conclusion. Yes. Yeah, that's my claim. So they can actually look different, but then they won't be.
And it's cut free, presumably.
And it's cut free. Yeah. You can get different cut versions of it. So yeah, they can look different. I've got some examples, but you need complex examples in order to witness this phenomena. I'm happy to go through it if you guys would like to. But essentially what can happen is, like, if I have many axioms and I have links, then there are various different ways that I can connect those links. One would be like a planar way of doing it, and then one might be a non-planar way of doing it. Now, that might look like it's actually not only different by the axiom links, but indeed it does, because you can move around the non-planar version, and then you just end up with something that looks exactly similar to the planar version, but all of the axiom links have been swapped around, right? So yeah, it truly is just the axiom links that are changing. And that's why we can specify a proof only using the axiom link permutation. That's all that you need. Alpha is the proof, right? Beta is an object that you use in order to check whether it's a proof net. So if I were to say that proof structures are now these alphas, then you should ask me what are the proof nets, right? And then what Girard says in his paper is that they're the ones orthogonal to, it's the orthogonal set, and then orthogonality is the cyclic condition. So literally, I give you a permutation. It's a pair of, defined by a set of disjoint transpositions, and then you ask me, is that a proof net? And then what I do is I just see if it's cyclic with all of the different bases corresponding to the proof of alpha. Does that make sense? So we're kind of done already. Like, these are the main observations. So now I've told you how the entire story exists inside the permutations world, except for like geometry of interaction itself. So there's yet a third permutation that you can define from a proof net that's got cuts inside it. And then that third one is going to actually give you the same one as alpha, corresponding to the cut eliminated version of it. Okay, so we basically just zoomed through the entire talk. That's fine. Maybe I'll do geometry of interaction, and then we can have more discussion and maybe look at some examples or something.
Oh, I think it would be good to do the non-zoomy version.
Yeah, sure.
I was hoping for that too.
All right, so what am I actually up to in that case?
I appreciate the zoomy version, but I also want the non-zoomy version.
Yeah, no, sounds good to me. I just need to actually work out what I've done. So I got Church-Rosser, I did the definition of alpha and beta. That's good. And then we did the example. Oh yeah, I need to convince you that we do actually get a reduction sequence. So yeah. So I'm defining for you a reduction sequence. Cool, so it's exactly what you would think it is. It's just a sequence of computational steps. And then I want to tell you that every single proof net, here's a point. Cut elimination does not hold for proof structures, okay? but it does for proof nets. So let me show you that. Can anybody think of an example of a proof structure that does not have cut elimination?
Mr. Cut after axiom, maybe?
Yes, good.
Or at least depends whether you count the empty set as a proof, I guess.
Yeah, that's a good point.
Or no, he shouldn't eliminate to zero. He should like eliminate to infinity, I guess. He's like the
That's the example I had in my mind, though. That's like, basically I had the exact same experience when I was learning lambda calculus, where it's like the first bunch of stuff that I learned on the topic was all of the bad examples before I learned any of the good ones. And so, yeah, that's the one that always gets inside my head. So you want to think. It's not going to be cut eliminated.
Is that thing actually lambda x in some sense? I never thought about this.
That's a really cool suggestion. I'm not sure at the moment.
Yeah, okay.
Yeah, that's cool. Okay, so this is easy. This is easy. We're going to induct on like the max complexity formula amongst all of your conclusions, right? So look at all of your conclusions, look at all of their complexities, take the maximum of such thing. That's the integer that I'm going to be inducting on. And it's easy because if they're a whole bunch of like tensors or pars, then they're going to be cut against each other, and you can just do that tensor par elimination step, and then you've reduced down to the base case. And so all you're doing is reducing all of the tensor par links until you get down to only axiom links, right? Axiom redexes, and then you want to eliminate the axiom redexes, and that's the base case, and that's the step where you actually use the fact that you have a proof net, right? Because if you have a proof net, then you know that that thing is like a long snake. It doesn't eat its tail, right? Okay. Such a stupid idea. I just wrote that sentence out and decided to use an ampersand for the word and, but it's probably not sensible. Okay. Oh, and what I mean by the conclusions is the ones that are getting cut against each other, right? So look at all of your, so they're not conclusions. So look at all of your cuts that you have to reduce, right? And then just pick out the set of them which all have the common max complexity across them. And if that complexity is zero, then you know that they're all axiom links and you've reduced to the base case. And if it's non-zero, then they're necessarily tensor par links, and then you just go ahead and perform that and you've reduced the complexity.
I am not sure about that. In the cut reduction, the sort of case where when you're cutting a tensor against a par, what if, say, the par is not like two other formulas that have been parred together, but it's just part of an axiom link?
Yeah, fair. I guess I'm implementing atomic axioms, right? So I'm using eta. I would use eta equivalence in that case. So I would be like, I would replace that axiom with the atoms that then par together to form that par link.
Okay.
So if you wanted to...
That seems important.
That does seem important. I think that mine implies yours though. If you take yours and then you perform the Ada reduction steps that I just explained, and then you perform cut elimination on that. No, that could feed up. And I thought maybe that would just stay there and then you could ignore it. Yeah, okay, fair enough. I need to mention that. Okay.
So when you say the final thing is cut free, it's really like also complexity free. Like it's all atomic.
Not if your original proof net had tensors and pars that weren't cut against anything. So all of the cut tensors and pars have now been reduced.
Right. But looking later on, like you talk about the sort of chain of axioms and cuts of like atomic formulas.
Yeah.
Is that just part of the proof structure and there's other stuff?
Yeah, so you could have one of these chains of axiom and cut links, and then you can have another one. And then between the two tails, you could have like some tensor link built up or something. And you can have a combination of those. You can build up a complex tensor link. And that's fine. That's not going to be eliminated. Like the chains of axioms is just going to become single axiom links. So take any cut-free proof structure. It's going to have could have tons of tensors and par links inside it, and then take one of your axiom links and then just build that up to a chain of axiom and cut links. You perform reverse axiom reduction, and then you have an example. They're all axiom redexes, then you can obviously eliminate the axiom redexes in any way that you desire. Cool. Any questions on that?
Yeah, I'm still a bit confused about the atomic axiom links thing. So just conceptually, if we're talking about assigning, I mean, if you say proofs are permutations, I guess you must have in mind from the beginning that you only allow atomic axiom links. Is that right? Otherwise, it seems like a proof is maybe multiple different permutations depending on whether you apply Ada reduction or not. But then Ada reduction wasn't built into your definition of proof nets as an equivalence class thing. So.
Yeah, okay, that's a really good point. So I'm assuming atomic axiom links from earlier than I even realized, but I definitely am doing that for exactly what you just said. I agree with you that that claim is going to fall down if you don't have atomic axiom links. And in fact, this is, I should have noticed that. This is in multiplicatives anyway. I guess I started thinking about it from that perspective and, forgot that I was thinking about it like that. But whatever, yeah, take the atomic axiom links, which you can always do. That's just a standard eta reduction concept. And then everything that I've said makes sense. Everything's well-defined. This proof works, etc. Cool, good observation. Okay, sweet. So yeah, we've now got cut elimination. We now have the different permutations. We've seen, I can write the definition of the sequentialization theorem. Oh, I keep doing that. So I just want to take the set of all of these beta permutations corresponding to pi. I'm just defining this set because I'm about to quantify over it. So we get the sequentialization theorem. Cool. So now I've got the sequentialization theorem that only uses the language of permutations. This is literally the same thing as the long trip condition. So if I have a short trip, then I can take the permutation defined by the axiom lengths and the permutation defined by the beta lengths, and there's going to be some small loop that doesn't cover the entire proof net inside that. That's true if and only if I have a short trip. That's going to give me a non-cyclic permutation. It's exactly equivalent. It's just a change of language, nothing more. Okay, let's do geometry of interaction. Okay, this is the most difficult part of the talk. So I'm going to define a third permutation for you. And it's going to look very weird, but then I'm going to make it make sense, hopefully. Just let me boost it into my head.
That has an interesting double meaning.
Well,
I'll use my boot to put it into your head.
thanks, Dan. That's really well. It wasn't actually a call for audience participation. All right, cool. Yeah, that's right. Okay, so here's where I want to use that object that I was talking about earlier, right? So, and this explains on a more technical level the claim that I made earlier where the axiom Redex steps are the ones that you want to pay more attention to. So what I'm going to do is I'm going to take a proof structure with cuts, right? And I'm going to reduce all of the tensor par lengths. So all that we have are these axiom Redexes left, right? Okay. And so then what we're going to end up with is a whole bunch of these chains of axioms and cuts, right at the tree, the leaves of our tree. And then what I'm going to do is I'm going to say, look at like the endpoints of these chains, right? So if I had one of these chains, assume that it starts at AI, say, and then it ends at, you know, not AJ. And then I'm going to send I to J. So what we're doing is we're going all the way through those chains, right? And that defines for us another permutation. Now, clearly that permutation corresponds to the cut-eliminated version of it, right? Because all the cut-eliminated version does is it deletes all of those interior axioms. So that's it. It's super simple.
Isn't that kind of half cheating to half do the cut elimination and then say, oh, I'm assigning to the
I was hoping this
something?
question would come up. No, I'm well prepared for this question. So that's okay. So this is a discrepancy between the way that Girard does it and the way that I do it, right? So Girard doesn't perform half of the cut elimination steps before defining the permutation, right? But when I did that, the permutation became so much more transparent, right? So I'm doing this for a semi-pedagogical reason, but you can perfectly the same do this without having performed some of the cut elimination steps. And the reason why is because you can actually infer the former from the latter, right? So if I had okay, so I had that cut link, right? Then what we're going to do is we're going to say, well, I can actually read what the axioms are going to end up being cutted against each other from this. I can see that since I have A tensor B and not A part, not B, that A is getting cut against not A, right? So there is a corresponding, so there's integers here, right? If that's I and that's J, then what Girard would say is you look at this cut and then you're going to map I to J, and you do that through, and then what you do is you take, that defines an integer, and then you take the least such integer so that there are no, wait, sorry, let me get this right. No, just retract my final statement, and then everything that I said is true and makes sense. So he's doing what I've done, right? Where if you just do the cut elimination corresponding to the tensor par redexes, then you get in an explicit and formal way the like atomic components of these formulas that are related to each other, right? And he just kind of says, like, you have this, but I was trying to set it up formally. And so I did that by, like, you know, if you were to ask me what are those things, I'd say they're the ones that you get when you perform the tensor par cut elimination. So that's why it ended up in my definition.
Did you write your definition?
I haven't written on the board, but it's in my notes.
Right.
I'm just about to.
Yeah, I guess I'm 80% convinced.
Well, 80 is something. Okay. Wait, am I looking at proof net here? Yeah, proof net.
I hope this doesn't feel like a PhD defense or something. I know we're participating.
Oh, they always do. No, no, no.
Seminar.
No, this is good. This is where you learn stuff. All right. Yeah. Yeah. So this zeta is that proof that I'm talking about. So we've just eliminated all of the tensor par cuts, and now we've got zeta, which if it has any redexes, they're axiom redexes. Yeah. And then I'm going to look at the cuts, sorry, not the cut, the axiom permutation corresponding to zeta. I want to leave that up. Can I erase this side of the board?
Yeah, fine with me. Yeah, I just thought through what the right way of cooking up this permutation is, and I guess that's exactly what's in GI1.
Yeah.
Right. I mean,
how so?
Well, what you want to say is, okay, at the end of the day, you want a permutation, fine. But in the intermediate steps, it's not exactly a permutation, right? You want to define some local things which you compose together to get the eventual permutation on the axioms, which means you need to associate to the par length something a bit bigger and an operator on that, and then multiply them all together. But that is what GOI wants.
Oh, that's cool. Oh, okay, that makes sense. Yeah, but you also want the other connectives, right? Like that's the part of the story that I'm kind of more interested in at this point. I'd love to see how this works with the exponential link, which is like the part that I'm stuck on with GOI1 at the moment. Okay. Okay, so this is another permutation. This is not the permutation. I'm going to use this to define the permutation, but it's an intermediate object. It's just the permutation corresponding to the cut lengths associated to zeta, right? So in exactly the same way that alpha gives you these transpositions via the axiom links, I'm just doing the same thing with the cut links, which exists because we have no tensor par links. Cuts, sorry, no tensor par indexes. M is my index.
just realized, Will, that I made a mistake with regards to the time for the seminar. So it's advertised at 11, but then I thought it was 10 yesterday, and that's what I posted on the Discord. So I want to apologize to you.
Is that what
it's just
people rocking up? That makes sense.
Yeah, so that's my mistake. I'm sorry about that.
No, that's okay.
The time is 11, so in the future it's at 11, but I got mixed up somehow yesterday. So
it's really odd because I was debating all morning. I was like, was this at 10 last time or was it 11?
Yeah.
I just couldn't work it out.
I don't know why it ended up with 10 on my calendar. So yeah, sorry about that.
No worries. It's all good. Okay. So, I mean, we're right near the end now. Let's get this finished. Okay, so what I mean by this is inside zeta, you've got all of these chains of axioms and cut links, and I'm going to just come up with some random notation, it doesn't matter, to denote the ones that are on the ends of all of these, right? And then using that data, I can define a permutation for you. So then we do so for each I, okay, and this is the important formula. Okay, so what's going on here is gamma.
Sorry to interrupt you. Well, when you say the permutation corresponding to cut links, so that's defined in this. I mean, that's like a one-step thing, right? So I go from an index, and what exactly is the definition there? Sorry.
So just recall that zeta at this point doesn't have any tensor par indexes, right? So all of the cuts are against axioms, yeah? And so that defines a disjoint set of transpositions. So if I had AI cut against not AJ, then IJ is part of my permutation. And then if
it's part of gamma, right?
That's gamma. That's what gamma zeta is.
Yeah.
But then when you think about it if you're thinking about these chains as being sort of cycles in the permutation, don't you also need to add the axiom as well as the cut steps to connect them? Or
yeah, that's what the composition there is. Alpha pi.
Yeah,
gamma,
correct.
Zeta.
Oh, I see. Okay. Okay.
I mean, this is actually zeta anyway. Yeah, but that's exactly what this is doing, right? So what I'm going to do is this minimal integer di just is guaranteeing me that we're landing at the endpoint, right? That endpoint is the thing that's going to survive the cut elimination process. And so that just becomes an axiom link. And so this is alpha of the cut eliminated version of pi.
Wait, do you want to plug in I there or KI?
Oh, good question. I think it's
Because
KI.
later you do plug in KI, so
Yeah, I think it's KI. I doesn't make sense. Yeah. Cool. Yeah, that's right. So all I'm trying to do is guarantee that we have a permutation on the set 1, 2, ... up to m, right? But it's just not the case that these axioms that I've picked out are ordered like that.
0 an integer?
Pardon?
Is 0 an integer? I think di equals 0 is valid in what you wrote.
Yeah, I believe so.
Well, then you want to say di positive, right? Otherwise, you just stay at the end where you are.
Yeah, but like,
Shut up.
isn't that dealing with the case where you just don't have a cut? Like, what if I have? Then this guy's going to just move to itself. So Ki has to map to Ki, which I guess
that's using the
the
gamma, right? I'm just saying that this formula, if I take di to be 0, the left-hand side is always just Ki. So,
but I'm saying that that's what you want in this case, right?
But it's always true.
But you don't want it in the other case.
Oh, I see. Right. Yeah, so we do want... Oh, what have I done?
In that case, you want di equals 1, don't you? Isn't that alpha?
Yeah. Yeah, that's just going to be alpha. Yeah, that makes sense.
So you just want to say di greater than or equal to 1.
Yep. Agreed. Okay, cool. And then I can define this permutation.
Are the atoms at the end of the chains, are they always part of an axiom link, or could you like do axiom cut?
They're always part of an axiom link. Because how could it not be part of an axiom link, right? Like if I've cut against something, I've cut against something, and this thing is either atomic or not. If it's not, then that betrays the assumption that we don't have any cut redexes that are tensor par, and so it has to be atomic. And so if it's atomic, it has to have been introduced by something. So it has to be connected to something else by an axiom link.
Yep, okay.
Okay. I might use a different axioms. So I'm just saying xi is the normal form of pi, and the normal form is just the cut-eliminated version of it. Okay, and then you get the simple formula. Cool. And that's like truly directly just by construction, right? As we've already established, what this formula here is doing, or what this di is doing, is it's just connecting your atoms to the atom that it's going to end up being connected to once you perform the cut elimination process to those chains of axiom and cut links. So these two permutations are literally the exact same thing. Okay, any questions about that?
Cool, but it feels like this is not what does the theorem say? I mean, you said geometry of interaction, and this is the main theorem. Okay. What do I read? What's the sense of this equality in Frege's words? I mean, what is the content of saying these two things are equal? I mean, I'll express my, sorry to interrupt, I'll express my kind of devil's advocate dissatisfaction with this equality, which is, if I have in my head this proof net and its chain of reductions, then this equality basically just summarizes my state of knowledge in some sense. I mean, that's how you've argued for its truth. But if that's already in my head, it's not exactly impressive as an equality, right? It's just like, okay, this is one way of writing down the content of that reduction.
Yeah, I don't think that anything deep is happening on the level of the permutations. It's more the interpretation of proofs inside the world of interpretations that I think is the significant point. I mean, we had the sequentialization. Sorry
to interrupt. You just said interpretation of proofs inside the world of interpretations. You mean the world of permutations?
Is what I mean. Yeah. So to me, it's like we've got these two theorems in the world of proof nets, right? One of them is the sequentialization theorem, and one of them is cut-elimination. And then I went through the sequentialization theorem, for permutations just before, and then this is cut-elimination, right? So I mean, even cut-elimination in proof nets is not a significant theorem, and so this is the reincarnation of that inside permutations. Maybe you prefer the sequentialization theorem even, but maybe you could play the same card for devil's advocacy there.
I just feel like it would be more impressive if one side of it was defined entirely in terms of the unreduced proof net and the other side entirely in terms of the reduced proof net. So the right-hand side is something that's defined entirely from the normal form. The left-hand side feels like this thing that's kind of sort of to do with the unreduced thing, but maybe not really, because you're kind of relying on the reduction in various places. So it feels like the proto version of a theorem. I suppose the real theorem is what geometry of interaction is in the later papers, maybe. But
that's what I was just about to say, right? So you could go ahead and come up with a definition of delta just from the completely unreduced thing, but then you just put in your mess elsewhere, right? It's like, well, the way that I'm going to define that is I'm going to have some really ad hoc way of following a complex formula back to its atoms and then constructing a permutation from that. But that process of going back through to the atoms it's going to be your tensor par reduction, whether you admit that it is or not, right? And so what you want to do is you want to come up with a statement like this, where on one side of the equality, you've built it from the way that you built the proof net, right? And this is what geometry of interaction 1 does exactly. So like maybe this is the most important realization of this paper, is that when you look at this, you say, this is nifty and certainly works, but it shows the lazy lens that we're looking at the problem through. It's like, it's not really this that we're after. What we want is a mimic of the building of the proof structure inside your realm of interpretation, be that permutations or be that bounded linear operators, right? Which kind of makes sense. That's kind of the philosophy of geometry of interaction, I think, because if you compare it to like denotational semantics, for example, it's just kind of like, here's two interpretations, one of the proof with cuts and one without, and they're just exactly the same thing. Whereas geometry of interaction will give you two different things and then relate the two of them together. And so geometry of interaction is kind of looking deeper than denotational semantics. It's looking into the way that you built the proof structure, perhaps. So I'm kind of expecting to get out in geometry of interaction 1, but I'm not certain on that yet.